Other questions?
When you computed this diameter of this,
Yes.
then you did an integral from lambda large scattering to lambda now.
Yes, that's right, yeah.
And that you approximated to be 1 by h0.
Yes.
Why actually? Because h0 is the dominant contribution.
Well, this calculation we had done earlier, right? And basically what happens is that this integral gets contribution only from the current epoch. Most of the contribution comes from the current epoch, right? That's why you get this 1 over h0, right? But this is something that we had, if you recall, we had done this calculation earlier, right? It's yeah, because it's basically d lambda over lambda times lambda dot, right? And lambda dot has an h0, and everything else is just some numerical factors, right, in that integral. So you had some integrals 0 to 1, right, of some numerical factor, and then there's a 1 over h0 that scales out.
Why are we describing all this era using scalar? Is it because it's a simple model thing?
Yeah, scalar field model is the simplest model of inflation because you want to, I mean, you can, if you want a potential, right, you cannot write a potential for a gauge field, for example, right, because it will break Lorentz invariance, it will break gauge invariance. So the scalar field is the simplest model, but the scalar field could be composite in principle, right? It could be a bound state of other fields.
In the potential that we C/φ, there is a small constant area, then there is oscillating part. But this before this constant area, there is also a small.
Yeah, but that we started with that. But then we also showed yesterday that if we just take a standard a phi to the b, right, that also does it. That doesn't have that flat region, right? Nevertheless, for large enough phi, right, there is you can identify a region where it behaves as if it's a constant phi, constant v, right? Even though v is not really constant for large phi.
We just don't have to start with any kind of homogeneity.
Exactly. Yeah. I mean, the point is the store role condition is satisfied even when V has that feature, that form. Any other question?
And how do you incorporate this reheating part on this A phi to the power B model?
Yeah. So reheating basically, I mean, the beginning of reheating, right, will be whenever the store role condition stop being violated, right? So if the phi is rolling from a large value to a small value, right, at some point the store role condition breaks down because we saw that the store role condition requires that phi is larger than something. So that is the start of reheating, right? Then phi reaches the minimum. Okay? Imagine that you are just taking m square phi square, right? Then phi starts oscillating around the minimum, right? And then that converts the cosmological constant to matter, and then phi decays into radiation. Okay? So that's the process. So in this m square phi, if you take things like m square phi square, then reheating is basically the part of the same oscillation, right? Same movement, except that it is now close to the origin.
And then this suggests that if you take the power to be very large, then that's probably not good for reheating. Flatter and flatter and flatter.
Yeah, true. So m square phi square is the standard, is all of things, standard things, but you can also take the sum of terms, right? Yeah. We just took the for a simple example a phi to the b, but that's not necessary. You can take m square as the standard lambda phi to the fourth theory, for example, right?
You can also take some other function.
Yeah, you could take some other function, right?
Suppose that b is equal to 2.
Yes.
Then, because the last fourth condition will require a to be very small.
Yes.
In that case, wouldn't, and if we see the region near the minimum, wouldn't it be almost like a flat mesh?
Yeah, so a should be very small. That means that the particle mass is small.
Yeah, so locally it will be very like a flat.
Yeah, it will be like a flat region, right? But it's not going to inflate there, right? It's flat, but it's still large enough. See, the a can be small, but if it's, for example, if the inflation was happening at say 10 to the 16 GeV, right? Maybe a is like 10 to the 10 GeV, right? It's still a very large mass, right, from our perspective. So it will basically convert the cosmological constant into particles of 10 to the 10 GeV mass. right, or 10 to the 8 GeV mass, which will then decay into radiation, and then the standard Big Bang physics starts. Right, so indeed, it is true that if A is small, then the particle masses will be small, but it's small compared to the inflation scale, not small compared to our scale. Any other question? Okay, so now we are going to discuss this reheating process a little bit. Okay, and using some simple model. Okay, so reheating is a process by which the energy that was contained in the scalar field potential, right, as we saw, that first gets converted to standard matter, right, non-relativistic matter. Okay, but reheating is a process by which that non-relativistic matter gets converted to radiation, okay, by decay of this phi particle. Okay. So this is the conversion of matter to radiation. At the end of inflation. Okay. So we'll take the simple model where we'll assume that the energy density gets contribution from two sources. One is a matter source, that's the phi particle, right, and the other is a radiation. Okay, we will not try to distinguish between different components of the radiation. Okay. So energy densities is rho phi plus rho radiation. Okay. And then we will capture the fact that rho phi gets converted to rho r, okay, in this following equation, the ddt. Okay, so first of all, let me write the conservation equation. So rho phi plus rho r lambda cube should be minus 3 p phi plus pr lambda square lambda dot. Okay. But p phi of course is 0 because this is matter. So minus 3 pr lambda square lambda dot. This is the first equation. This is the standard energy conservation equation, the total energy conservation. Okay. But the second equation that I am going to use, P phi was?
Oh, phi is matter.
Yeah, because cosmological constant has gotten converted to non-relativistic matter, right? That's what it is said. That once the field reaches the minimum, right, then it starts oscillating, and that's matter. That is just phi particle, right? Non-relativistic phi particle, right? So that is what we are treating as matter, right?
Phi was inflaton.
Yeah, phi was inflaton, but the same inflaton can behave like a matter.
Yeah, but then for the inflaton, the equation is saying is rho equals minus 3. And then that.
But that is only when the slow roll condition is satisfied, right? Once the slow roll condition is violated, right, then it's like a scalar field oscillating. Well, maybe there is of course a transition. It doesn't happen suddenly that P goes from non-zero to 0, right? But that happens during the rolling of phi, right? And after that happens, P basically becomes 0, right? Once phi starts oscillating, right? As long as the phi is just moving, rolling down, right? P is non-zero, but once it starts oscillating, it becomes P becomes 0. On the average pressure is 0, right? And that we said we can interpret as if it's a collection of non-relativistic phi particles, right? Because phi particle has mass, right, which are present at the end of inflation over time, right? Yeah, of this oscillation. So what we had seen earlier, that if you write down the expression for the mass, the energy density and pressure of a matter of a scalar field, right, and let it oscillate around its minimum, right, then the average pressure is 0, average energy density is not 0. Right? Time average pressure energy density, and the interpretation of that was that this time average pressure being 0, it reflects that it's a collection of massive scalars, right, which have almost 0 velocity.
This happens for all potentials.
This happens for all potentials. Yeah, meaning as long as there is a non-zero minimum, right? As long as the m square is non-zero at the bottom. This is the same thing as the axionic dark matter, right?
So is the statement that if you have a x squared minimum, then you can do this?
Phi square minimum, yes.
Yeah,
Phi square minimum.
Parabolic, I mean, if the minimum is of order like say x to the 4, phi to the 4, then the
Yeah.
statement would be true.
Yeah, that's right. I mean, because then there will be a massless particle, right? We don't want a massless particle remaining at the end of inflation, right? So there has to be some m square phi square component, right? On top of that, there may be lambda phi to the 4 interaction. Okay. So this is a point that we assume that at the end of inflation, right? That's this part, right? Here, okay, is this oscillatory field. Okay, the spatial gradients are all 0 because inflation has smoothened it out. Right? So there is no momentum. Right? So this is really the oscillate type, the space independent, time dependent oscillation, and that we had seen that classically it produces average P equal to 0, average rho non-zero, and that has a simple quantum interpretation that because these are 0 momentum particles, right, their pressure is 0. 0 momentum massive particles.
This approximation of replacing actual pressure by its time average, this is good here because the particle is very massive.
Yeah, but we are talking about 10 to the 10 GeV
So the frequency of oscillation
upwards. Exactly.
the time period will be very small.
That's right.
Replacing by the
Yeah. Okay, so the second equation is how the energy density is getting transferred from the phi to radiation. Okay. And here I'll just use a simple equation which is minus gamma times rho phi lambda cube. Okay. So gamma basically is the rate of decay of phi particle to radiation. Okay, we will not try to include the reverse reaction, right? There will be always some small probability that the radiation will produce back the phi particle, but we will just ignore this. Pardon?
The PR derivative part will be on the same.
No. This is one. This is first equation. This is second equation. Right? Second equation tells this is a total energy conservation. Right? Second equation is telling us how the energy is getting depleted from the phi particle. Right? As the phi start decaying to radiation, right? The energy content in the phi particle will be depleted. Right? Of course, it will go into the radiation because the total energy is conserved by this. Okay. So this equation has a simple solution. So rho phi lambda cube is, let me call it rho f lambda f cube okay. So Tf is the end of inflation and rho f is the energy density lambda f is scale factor at the end of inflation. Okay. So the picture is that at the end of inflation, all the energy density have gotten converted to matter energy density. Right? We are calling that rho f is the matter energy density. Lambda f has the scale factor at that time. Right? Tf is the time at which that happens. right? And after that we evolve it using these two equations to see how the energy density is getting transferred from matter to radiation. Is this clear? TF. Oh, by following the phi particle motion. The phi motion you have written down the equation for phi, right? That phi double dot plus 3h phi dot plus v prime phi equal to 0, right? So you can roughly you can say TF is the time when phi reached 0. If you use a phi to the b, right? You can think of this as when TF phi reached 0, right? Because then it starts oscillating. Yeah, because it just starts oscillating, right? This is the TF is the time when the energy density has gotten converted from cosmological constant to matter, right? And you can roughly you can take that to be the time at which the phi reaches 0, right? Because once it reaches the minimum, right, then it starts oscillating.
V of phi is reaching the value. Phi is some finite value.
Yeah, phi has finite value, but well, if you take this a phi to the b, then v of phi is minimum at phi equal to 0, right? Okay, but for any other potential, yeah. So when v of phi is minimum, so when phi reaches the minimum of v of phi, right, that's when you can count as your TF. Right? Because roughly that is the time when energy got converted to matter. Right? Because the phi now starts oscillating around its minimum.
Gamma is calculated from all the decay processes that we
Yeah, gamma you can calculate if you are given the Lagrangian, right? Describing how phi couples to the standard model particles, then gamma is just the total decay cross section. Right? So you can calculate from the microscopic physics.
This is the gamma particle to all standard model particles.
Yeah, gamma particle to all standard model particles.
So here radiation means all the standard model particles.
Yeah, all standard because they are all massless at this order, right?
But to determine gamma, we need the coupling constants in the Lagrange.
Yes, indeed. So you have to write the Lagrangian.
Yeah, but do we know the value of the coupling constant?
No, because we haven't even seen the phi particle, right? Yeah, so you have to find use your model, right? Again, if you have a microscopic theory that you have gotten from some other sources, right? Then of course you know everything, right? So that's one philosophy. Otherwise, you say that okay, you try to put some arbitrary coupling and put limits on those couplings, right? So that you get what you want. Because at present you only know physics up to scale about TeV or less than TeV, right? I have say 100 GeV, maybe 200 GeV. Okay? Anything beyond that we don't know, right? So that's something you have to guess, right? And basically you guess it by saying that you want to adjust the coupling so that you produce the universe that we see. Is this clear? Okay. So this, as I said, you can solve this. The first, this equation of course has the solution, and then we can substitute it here to solve for rho r, right? So the equation 1 can be written as d dt of rho r lambda to the 4. Okay, this is the same trick that you took this. You write PR equal to rho r over 3, right, and take it to the other side. So this gives you lambda times rho phi. Yeah, lambda to the 4 because this minus lambda square lambda dot minus rho r lambda square lambda dot you can take to the other side. See, suppose rho phi was not there. Yeah, PR is rho r. If rho phi was not there, right, then you know that rho r lambda to the 4 is constant, right, and that you can get from here by taking to the other side. So same trick we are doing here. Okay. The only difference is that now right hand side is not 0. That is lambda rho phi, right, which is lambda lambda rho 5 lambda cube, which is lambda rho f lambda f cube sorry, this is not, this is d dt of rho phi lambda cube. Okay, because this d dt of rho phi lambda cube is what I am talking to the other side, right? Should be negative, yeah. So, pardon?
It is minus d by dt of rho phi.
Yeah, minus d dt of rho phi lambda cube, right? But the overall, this lambda is multiplied because this d dt of rho r lambda to the 4, right? Otherwise, I should have written 1 over lambda on this side.
T minus TF.
Pardon? T minus Tf, yes, thank you. Okay. So this tells us that rho r lambda t to the 4 is given by lambda rho f lambda f cube integral Tf to T dt prime lambda t prime and I think there is a gamma here. Here also, yeah, there is a gamma here. I just integrated this, okay, and I used the fact that at t equal to Tf, right, everything was in the matter, right? So rho r was 0. Okay. That's why I am integrating from Tf to T. Is it clear? So rho r, let me write the expression for rho r, gamma rho f lambda f cube lambda t to the power minus 4 integral Tf to T Okay. So this of course goes to 0 as t goes to infinity, since lambda of t goes to infinity. This is a finite integral, right? Because of this gamma, right? This integral is finite as t goes to infinity. Okay. And then we have this lambda to the minus 4 which is falling, right? Because it's now matter and radiation dominated, so lambda starts increasing. So lambda to the minus 4 falls, okay, which basically means that if you now plot rho r versus t, right? Suppose this is Tf, right? It starts increasing from here and then eventually it goes to 0. Okay. So at some point it reaches a maximum.
That depends on lambda t's functional formula.
But lambda t grows, right? Lambda always increases.
Yeah, so if lambda t were say Gaussian or something.
Oh, this one. Oh, this one only grows as power law at most, right? After inflation, it's radiation or matter, right? So it grows as power law, right? Okay, there is a cosmological constant, but that is very, very tiny. Okay, so this part is really a finite integral, right? And so this makes it go to 0. Okay. So this peak value, if you call this rho r, capital R, right? We define the reheating temperature Tr via rho r equal to half AB Tr to the 4 times n. So this is the effective number of degrees of freedom. Okay, which counts 1 for boson and 7, 8 for fermion. Okay. So this is in a sense the definition of the reheating temperature, because this is the maximum temperature that you will get after inflation. Yes.
Lambda, if lambda is positive, the other was positive.
How rho r is going to 0? Oh, because this integral is not going to 0. Integral is going to finite. This lambda t to the minus 4 is making it go to 0. Yeah. Is this clear? This definition is clear? Right? Why did it have to rise up? Oh, because it's positive integral, right? For finite t it's positive, and at tf it was 0, right? So it has to rise and it remains positive, right? So it basically rises and falls, right? You can say, okay, in a very strange situation you may have rise and fall, right? But for monotonic lambda it doesn't really happen. Right? It starts rising and then it falls. I think there's an oscillation, that's what I'm saying. It always remains positive, that's clear.
So this is the entire integral, right? I mean, integral times lambda to the power minus 4 is rising and falling, right?
Exactly. Yeah. Because this goes to a finite value, right? But because of this lambda to the minus 4, it's falling eventually.
For most lambdas,
Yeah, so rho r reaches a peak value at some point, right? And for any rho r, of course, you can define our TR by this relation, right? Because that's a formula for radiation, right? That the temperature of the radiation is related to the energy density by this fact times the effective number of degrees of freedom. So you calculate TR, right? And this is what we call the reheating temperature. Okay? Because this is the maximum temperature radiation acquires after inflation. Okay? And this is the temperature that has to be large enough so that you can create baryons after this, right? Or create B minus L after this.
just a number, right? Some pi squared.
Yeah, AB is pi square by 15, I think. It's probably pi square by 15. Yes. Yes. No, all the relativistic particles, yeah, exactly. And because we are assuming that they are equilibrium, right? So they share the energy, because standard model we know that above 100 GeV everything was in equilibrium, right? So there is so it's radiation means everything.
So this means like entire energy contained in the pi won't get converted into the radiation.
Well, the point is it will convert, entire energy content will convert to radiation, right? But what's happening is that energy density is also falling because universe is expanding, right? So if for example everything was converted to radiation immediately, right, then the reheating temperature would have been higher, right? Because earlier it reaches the peak, the higher the reheating temperature is, right? It's the question of the efficiency in converting matter to radiation, right? If it's less efficient, right, then it will take longer time, right? So that means if gamma is small, it will take longer time, so the reheating temperature will be smaller, right? Because by the time the energy density has gotten depleted, right? If it happens almost immediately, if gamma was very large, right, it will happen almost immediately, and then the reheating temperature will be higher.
That says something about the x coordinate of the peak determining the y coordinate of the peak. Right? That's what you just said, because it starts earlier, then it should be lower. Sorry, higher.
Yes. Because the total energy density, right? This equation is always true, right? So if everything became rho r immediately, right, then it will rise, okay, and then it will follow the 1 over lambda to the 4, right? if it got delayed, right, this process, right, then it will again rise and reach some peak value, but by that time the energy density has gotten diluted, right? Some in the form of matter, some in the form of radiation, but both get diluted.
What period of time?
Yes.
Since radiation, due to the expansion, radiation falls on 1 by lambda square, and since it has not come, phi density has not completely become zero, over the period of time we should be able to see some
From phi. Yeah, but upon gamma is microscopic, right? So that decay rate is very, very fast, typically, right? So yes, it will be exponential suppressed density of phi, if you say, right? Because phi is decaying out with this rate gamma, right? That will get depleted very fast. So it's like having an unstable particle, right? In the early universe, right? Those unstable particles, yes. So there will be some unstable particles, but most of them would have decayed, and the density of such unstable particles falls off exponentially.
This integration, I can evolve it up to t equals to.
Yes, this equation you can evolve up to infinity, but
after one time in our universe it is cosmological constant dominated. I have this exponential.
yeah, but these integrals get saturated very fast, right? Because this gamma, right, as I said, it's a microscopic value, right? So it gets saturated very, very fast, right? In terms of time scale, right? It's like say 10 to the 10 GeV inverse, right? That's the kind of time scale we are talking about.
It's the behavior of the Laplace transform of lambda. So
Yeah, right. So it basically is like the by t minus tf of order 1 over gamma, right? These would have fallen off, right? Because it's exponentially decaying. I mean, how much phi is there you can see from here, right? This is, that's even a simpler equation, right? This tells us that the phi particles are getting depleted, right? First of all, there's a 1 over lambda cube depletion, right? That is always there, but it's also getting depleted by this exponential factor, right? And that, so for t much larger than 1 over gamma, right, this factor is very, very small.
Something like we know from the standard model physics and so on, like up to one time, up to nucleus and so on, we know very well. Then so all this process should happen within that just after inflation to before this. Like,
Yeah, exactly. Yeah, right.
By that time, all this decay
everything would have happened. Yeah, right. But typically that would happen because phi, if you take of the order of 10 to the 10 GeV, right, its decay rate will be very, very fast typically.
do we have predictions for these this reheating temperature?
No, we don't have predict. If you have if you give a microscopic model, you can predict. If somebody gives you a Lagrangian, right?
Yeah, given. Oh, okay. Then this would be a function of all the parameters
Of the Lagrangian, right? Otherwise, I mean, from experiment, you only know that TR has to be larger than the sufficiently large so that you can produce B minus L.
So how?
Yeah. So I think that we can determine TR exactly, right? Because it's just the temperature for the maximum value of rho r. So maximum value of rho r should be able to, I mean, we could write it in terms of the parameters of the Lagrangian, right?
Yeah, yeah. So if somebody gives you a microscopic Lagrangian, right?
Yes.
Determine TR exactly by explicit calculation, right? But we of course don't know what the microscopic Lagrangian is, right?
Yeah, but this there was this requirement for the temperature for baryonygenesis, right?
Yeah.
So I mean that would, I mean, can't we set bounds on the microscopic parameters? I mean, in reverse from that.
Yeah, you can, but you have to also have a model for baryogenesis, right?
Okay.
You have to have a B minus L violating interaction term in the Lagrangian.
Okay.
And then you will have a bound, right, which will involve all the parameters of the theory, right? So there will be a bound that if the parameters are such that the reheating temperature is too low, then that's ruled out.
What was the temperature for the B minus creation?
It has to be above standard model scale, right? That's all you know, right? That also has to be fixed from from your Lagrangian.
That's pretty large variation, right? 3 to 16. Or does it matter?
Exactly, yeah. If inflation happens at 16.
If inflation happens.
Yeah. Right. But the question is that I mean, you can using this you can try to reduce the scale of inflation because nobody really tells us that it has to happen at 10 to the 16, right? So you can try to reduce the scale of inflation, and that scale is in principle observable, right? Because we will see later that if inflation is the one that is responsible for all that is happening, right? Then the kind of perturbation you will have in the CMB, right, is sensitive to the scale of inflation. To the scale of inflation. Yeah, that inflationary scale, I mean, from this viewpoint, it looks like we don't know anything about inflationary scales, right? Inflationary scale, right? But the point is, experimentally, it is in principle possible to figure it out, at least put a bound, right? Because we know, for example, that inflation, the scale of inflation cannot be much larger than say 10 to the 16 G. Otherwise, you would have seen what is called tensor perturbation in the microwave background, which you don't see. Right? So there is a bound on how much tensor perturbation you have in the universe, and that sets the scale of inflation. That sets an upper bound on the scale of inflation. Right? So this is something we will see later. And it's a question of whether the fluctuations of the graviton were important. Right? We will see the density, the major part of the density perturbation is produced by fluctuation of the scalars, but of course gravitons are also fluctuating. Right? So whether the fluctuation of the gravitons are important or not, right, is determined by the scale of inflation. Okay, because gravity is produced by energy, right? So higher the energy, the more gravitational perturbation you will have. Right? And that would have left its imprint on the CMB sky.
That's the same that we would have seen in gravitational spectrum.
No, it's a statement that the CMB spectrum that you see, there's a photon spectrum, right, would have certain structure that we don't see. See, because gravitation, what will the gravitational perturbation do, right? It will basically make the gravitational potential bigger in some place, smaller in some place, right? Okay. But that in turn will mean that the effective temperature that we'll see will get affected, right? Because by the redshift process.
It won't have the 1 in 10 to the minus 5.
No, it will have 1 in 10 to the minus 5, right? But after the 1 in 10 to the minus 5, right, there is a smaller, so the gravitational perturbation is less than 1 in 10 to the minus 5, right? But how much less? That's the question, right? And it has distinctive signatures. So by looking at the sky, you can figure out whether the gravitational perturbation is there or not.
So this is even finer than 1 in 10 to the minus 5.
Yes, this is finer than 1 in 10 to the minus 5.
Attempts made to measure this one.
Yeah, it has there are attempts made, and people thought that they have found something, right? These biceps, so that if that was the result, that if that result was correct, then we could pin the scale of inflation to 10 to the 16 GeV, right? But then people found that that result was not quite correct, right? So that only gives a bound now, right? If it was above 10 to the 16 GeV, we would have seen it, right? But we don't know, since you haven't seen it, we cannot say what the scale of inflation is.
What is the scalar perturbation that we're talking about?
We'll see. I mean that will come because scalar perturbation, this phi is fluctuating during inflation, and that's what produces all the structure that we have.
This in the inflaton field.
Yeah, the inflaton field.
Actually, other than this
Quantum fluctuation. Okay, so let me just discuss two extreme limits of this. So one is fast reheating. Where gamma is large. Okay, HF is the Hubble rate, expansion rate at the end of inflation. Okay, because that's the standard scale which you should compare rates, right? Imagine that gamma is much larger than HF. In that case, here, this one makes things fall off sufficiently fast, right, so that lambda can be treated as a constant. right? Because lambda dot is controlled by h, right? So if this is very large, right, then lambda can be treated as a constant, so you can just set lambda equal to lambda f and take it out of the integral. Okay. So then I can write rho r as gamma rho f lambda f cube lambda t to the minus 4 times lambda f integral 0 to t, tf to t and this one is roughly, you can approximate by 1 over gamma for t minus tf larger than 1 over gamma. That gamma is large, right? So t minus tf larger than 1 over gamma still means t is close to tf. Okay. And you can approximate it by 1 over gamma. So this basically becomes rho f lambda f to the 4 lambda t to the minus 4. Okay, this gamma cancels 1 over gamma.
The correction terms in the lambda of t outside the integral you are saying will be relevant, but inside.
Yeah, exactly, right? But inside the integral, lambda f t prime, because this is getting contribution from t prime close to tf, right? Lambda of t prime you can just set equal to tf. So this is basically telling us what we could have guessed otherwise anyway, right? That it's as if the entire contribution, entire energy density got converted to radiation immediately, right? And then it started falling off as 1 over lambda t to the 4, right? Because rho f, because that basically telling us rho r lambda t to the 4 is rho f lambda f to the 4. So it's as if you had radiation from the beginning. Okay? The matter part, you just it just happens very fast that matter gets converted to radiation. Is this clear?
This is a rho f lambda f4, and what should be the value
What should be the value?
of rho f lambda f4? That numerator.
That you have to follow the inflationary physics, right? If you start from some initial lambda, right, it will tell you what it will be at the end, right? Or you work backwards, right? We know that today we have a certain temperature, right? And using that we can figure out that, so this will determine Tf, right? You relate it to half AB Tf to the 4, right? So when lambda equal to lambda f, T was equal to Tf, right? This you can find from the inflationary physics, right? Once you are given the microscopic parameters, you know what this number is, right? So you know what Tf is, right? And then you use the fact that Tf lambda f should be equal to lambda naught T naught, right? Up to these jumps in the middle, right? So lambda naught is 1, T naught you know, right? So if you know Tf, right, that is determined by the energy density at the end of inflation, you can figure out what lambda f should be. If you have a microscopic model, you know, right? If you don't have a microscopic model, then it's the same question, right? What is the scale of inflation?
Isn't that like, for example, the inflationary period, you know that this expansion should be equal 60 times.
Yes.
So what is the corresponding cosmological constant, and is that cosmological constant give some idea?
Exactly, that's right. Right. So the cosmological constant during the inflationary era is what is going to control the rho f, and hence Tf.
It's lambda 2 by lambda 1 ratio. Can we get anything about what will be exactly this cosmological constant?
No, that it's not determined, right? Because we saw yesterday that the lambda 2 over lambda 1, right, more than e to the 60, you can achieve with this scalar field potential, right? And that doesn't necessarily tell you what the cosmological constant is.
Some bound.
Pardon?
Some
So there's some bound. right? Because if you take the A phi square, right, then there will be a bound because there's a bound on A. Right? So that will tell you what the bound on the cosmological constant is, but not very much more. TF corresponds to lambda 2 roughly, yes, right? Except that I mean the conversion from slow roll to phi equal to 0 may take a little while, right? But otherwise it is lambda f is like lambda 2, what you call lambda 2. Is it okay? Any other question? So the other limit is the small gamma limit. Where you can basically ignore this term, okay, as long as T minus Tf is remains less than gamma, right? So and we get rho r is equal to gamma rho f lambda f cube. So here you see that this part is independent of gamma. That is some function of t. Okay, and if we plot f versus t, it will again have some maximum somewhere, call it fr. But the gamma dependence comes as an overall factor, right? So this will have some minimum or some maximum independent of gamma, right? So the reheating, so rho r is proportional to gamma in this case, right? And hence Tr is proportional to gamma to the 1 quarter. Okay, so this is basically reflecting the fact that if gamma is small, then the reheating temperature will be small, right? And the physics is clear. If gamma is small, then it's not converting very fast, right? And the universe is expanding in the meantime, so it's depleting the energy density. So smaller gamma means that smaller heating temperature. Reheating temperature is the maximum temperature the universe will reach after inflation, right? Where after that the temperature will start falling.
Do we have an idea about like, oh, this all should come from the microscope?
Yeah, if you are given a microscopic theory, you have an idea about everything, right? But you don't have a microscopic theory. So the idea is that we know that given a microscopic theory, this is what should happen. Then you try to reconstruct from what you observe as to what are the bounds on these various things, and using those you can put constants on the microscopic parameters.
Like, what is the lower bound we want the reheating to be? Because it should be something like.
That also depends on your model of baryon number violation, right? You have to see at what scale you want to produce B minus L, right? And the lower bound will be that scale.
More than standard models.
Yeah, you have to go beyond standard model, okay? But it's all connected. But once you try to do that, right, produce B minus L at a lower scale, right, then that will have some other effects, right, which may be observed today, right? So all of those have to be, so I mean you have many experiments and from particle physics, astrophysics, cosmology and so on, right? And so you have to combine all of them together and see what kind of bounds on microscopic parameters you can put based on that. So that's basically the principle that one uses, right? You try to look at what you observe and see what bound you can put.
When we say small gamma limit, we are saying like, compared to the even after the universe expanded to its twice its size, still there is not enough decay happening. So we will be able to see some 5 particles. We can put some.
But small gamma is still large gamma compared to what we can see, right? I mean, it's a relative scale, right? We don't want the 5 particles to be stable so that you can see them today, right? That will require the 5 particle lifetime to be the age of the universe, right? Okay, so that certainly we are not talking about that scale, right? Because otherwise the 5 particle could have served as dark matter, right? And in fact, in that case, the universe would have never entered radiation domination, right? If phi was stable, because it will always be matter dominated. Any other question? Okay, so now I'll start discussing the origin of fluctuation. Okay, because that's one of the successes of inflation, that it not only explains why the universe is uniform, but also why it's not completely uniform. Pardon? What happened? Oh, I see, okay.
Yeah, trying to.
Try to put a chat.
Hello? क्या हुआ?
Can't hear you. No.
No, I think you can.
I think Priyanshu, your mic is on. That's what they're trying to tell you. Okay. Okay. So origin of fluctuations. Okay. So here the idea is that the inflation, as we have seen, gives a smooth universe, right? The classical inflation that we have discussed, right, smoothens out everything. Okay. But we see fluctuations, right? We are not saying a completely smooth universe, right? If it's small, right? It's small in the sense that at the time of the CMB emission, it was 1 in 10 to the 5. Okay. Nevertheless, it's non-zero, and the question is what produced those fluctuations? Okay. So inflation smoothens. So what produced the fluctuations? The fluctuations that we see in temperature in CMB, right? If we look at different directions, it's not completely uniform, right? But there's a 1 in 10 to the 5 variation in this, and that is supposed to be responsible for the structure that we see, right? That small perturbation eventually grew to produce the structure in the universe.
Homogeneity and isotropy fluctuations, same everywhere or something. Fluctuations are same.
Yeah, the fluctuations are the same everywhere, right? The homogeneity and isotropy, yes. As far as we know, it's consistent with homogeneity and isotropy.
When you say fluctuation, please explain. There are numbers you mean like stars, galaxies, everything.
Yes, right. But that is a separate issue, right? Starting from that 1 in 10 to the 5 fluctuation in the CMB, right? There we know that the gravitational potential had a 1 in 10 to the 5 fluctuation, right, at the time of CMB. And then starting from there, you have to evolve it. Right? That's a classical evolution, and see if you can produce the kind of structure that we see today. Right? And basically 1 in 10 to the 5 is the minimum that we need to produce the kind of structure that we see. Right? So that way it's consistent with large scale structure, and the CMB fluctuations are consistent with each other.
Why do we need the fluctuation from the inflation? Even after inflation,
Yes.
so many mechanisms going on up to CMB.
Yeah, I'm going to discuss that, right? So whether those mechanisms can produce the fluctuation that we see. right? So the first guess will be thermal fluctuations after inflation. Okay, for example, the decay of the phi particles are creating those matter particles, so the nearly massless particles, right? So those nearly massless particles are basically carrying away energy from one place to another, right? And in that process, it will develop its own fluctuations, right? Because it's not all uniform. Because when a phi particle decays, right, there is always a probabilistic element there, right? In which direction it decays, and so that produces some fluctuations, right? And the first guess would be maybe those fluctuations are what is responsible for what you are seeing in the CMB. However, one can argue that those fluctuations cannot produce what we actually see. So if these are responsible for the fluctuations, right, then we know that these can carry information up to a distance that is 2 degree on the last scattering surface. Right, that is the calculation that we had done earlier, right? Horizon size. Horizon size determines how far light travels, right? So if these particles are carrying away energy from one place to another and producing these fluctuations, right, then those particles could only travel up to a distance of 2 degrees at the microwave sky. Okay. So this would mean that if we take averages, right, imagine that we take average energy density over scales larger than 2 degrees, then those averages wouldn't have the fluctuation, right? After the inflation, the problem is solved. The original problem is solved. Now there is a new problem, right? And the new problem is that now we are trying to produce the fluctuations after the inflation, right? Okay. That can happen by particles, the phi particle decaying, and the energy density is carried away in random directions, and that can produce, that random motion of these particles can produce a slightly more energy density in one place, slightly less energy density in another place, right? But that motion of the particles are limited within the horizon size. And this is the horizon after the inflation. The what got added, that delta RH, right? That is not included in this because it is happening after the inflation, right? So then you are back to this 2 degree problem, right? So this information is carried only up to 2 degrees, right? So this means that if we have done the averaging, if we have to look at the averages, say over 2 degree scale, and then compare the average here to average there, then there should not be any fluctuation, right? Because averages over 2 degrees should give uniform result, because the energies cannot be carried over a scale that is larger than 2 degrees. Is that logic clear? Right? So you cannot produce fluctuations at large distances, right? There is another way of saying this, that if you calculate correlation functions of the fluctuations, right, then this correlation function should be 0 outside 2 degree range, right? Imagine that we try to calculate 2 points in the sky separated by 10 degrees, right? You take the product of delta t here with delta t there, right? You get some number, some random number. Then you take 2 other points at 10 degrees. You again take delta t here with delta t there, right? And then you average over all these pairs, right? You should get 0, right? Because there is no correlation between here and here, right? But what one finds in actual practice is that it's not 0. In fact, fluctuations are scale invariant. That will make it more precise what we mean by scale invariant. But roughly, what one finds that fluctuations exist at all scales. Okay, not just that there is nothing special about 2 degrees. Okay, well, there is something special about 2 degrees. Okay, that we'll see, but otherwise the fluctuation exists in all scales. Okay. And this in fact was discovered even before people knew about CMB. or at least even before people knew the fluctuations in CMB. Okay. And the idea is that one could look at the structure that we see in the universe, right? And one could ask what kind of fluctuation in the early universe could produce this structure, right? And just from that analysis, people had concluded that the fluctuations must be scale invariant, that there must be fluctuations at all scales, right? Otherwise, we will not see the kind of structure that we see in the universe. So this is what is called the Harrison-Zeldovich spectrum. Okay. And this cannot be produced after inflation. Okay, because if it was the physics after inflation that produced these fluctuations, right, it will be limited to this 2-degree range, right? You cannot have produced fluctuations outside 2-degree range.
So, I mean, is it because we see objects in structures in sky which span beyond 2 degrees, and the formation we need?
Yeah, that the averages, right? If you look at this, because we see structure at various scales, right? Okay, there are small scale structure like planets and stars, and then the large scale structure, right? So now if you evolve them backwards, right, you find that you actually need initial seed perturbation also has to have fluctuations at all scales, right? Otherwise the kind of universe that will form will look very different from what we see. I think somebody is doing a project on this. Somebody asked me yesterday about you. Who asked? Yeah, for you I have sent the reference, right? Somebody else asked me about the structure formation. Okay, but so this is a separate study by itself, right? That starting from the structure that is small fluctuations that you see at the CMB scale, right? You evolve it forward, right? And there you really need numerical analysis because you have to use you have to solve the nonlinear equations. Okay, so now I can, whatever I have said, right, it can be represented in a diagram, and that's what I'll do in the rest of the lecture, and then I'll stop for today. Yes. In the microscopic theory. Yeah, so we'll do that, right? Because so far you don't even know how it originated, right? So you have to, so basically what will happen is that it will, I mean there are various ways of seeing it. One way of seeing it is that there will be a fluctuation in the gravitational potential, right? And that will cause redshift in the radiation, right? And that's what will show up as temperature fluctuation, right? But we will see later how to calculate this.
So one more question. So
Yes.
because inflation smoothens all fluctuations, so we want these fluctuations to survive that smoothing as well.
No. It will be produced during inflation.
During
Exactly. Right? Because in the fact that inflation smoothens all fluctuations is a classical description, right? But we will see that when we take into account the quantum fluctuations during inflation, right, it will actually produce these fluctuations. No, it also has the feature that because the spatial direction is expanding exponentially, right? If, for example, the phi here and phi there are there's some small gradient, it will just make the gradient 0. Right? So in that sense, it smoothens the fluctuations. Any other question?
It will be like 1 in e to the power 60 instead of 1 in 10 to the power minus.
Yeah, yeah. It will be, the fluctuations will be like 1 into the 60. It could be even larger because you don't know how long things inflated, right? E to the 60 is a minimum amount. Okay. So now let me just give some general results. So the point is that suppose consider any given epoch, right? Consider any epoch, and by an epoch we will mean the time in which lambda doubles, and that's roughly the kind of expansion rate of the universe, right? And this is of order h inverse at that time. H is the rate of expansion, so h inverse is roughly the time in which lambda doubles. So in this time, so in time h inverse, light travels a distance of lambda inverse h inverse. Okay, so let me explain this. Why is it lambda inverse h inverse? It's basically because of this fact that you have this dr equal to dt over lambda t. Right? So delta t is h inverse. So delta r is h inverse lambda inverse. So the significance of this number is that in any given epoch, right, the fluctuations created during that epoch can only travel this much distance. Right? So you can, so if you look at a given scale, right, and you want to ask whether a given scale, the fluctuations at a given scale received contribution from that epoch, okay, then you have to compare that scale with this. Okay. If that scale, length scale is larger than this, okay, then you know that at that length scale, you couldn't have that fluctuations at that length scale couldn't be affected by this epoch. Okay. So H inverse lambda inverse is the roughly the scale that sets the maximum distance to which fluctuations can affect. Is this clear? Right, because this is a light travel time during that epoch, right? Light travel distance during the epoch, okay? And you are always measuring in the co-moving distance, delta r. So let's calculate this in various epochs, right? So inflation, h is constant, lambda is c to the ht. Okay. So h inverse lambda inverse is c inverse h inverse e to the minus ht. Okay. So this falls as t increases, as t grows. Radiation dominated. Here you have lambda equal to a to the t to the half, okay, where a is a constant. So h, which is lambda dot over lambda, is half a t to the minus half over lambda. Pardon? Sorry, half t to the half. The lambda grows as a t to the half. Yeah, I have divided by lambda. So 1 over h lambda goes as half a t to the power. Something is wrong. It should have. Sorry, yeah. 2 a inverse t to the half. So it grows. Right? I just took 1 over h lambda and this came on the other side, 2a inverse to the half. Okay, the important part is the power of t. This 2 and then third is matter. Matter dominated. Is so lambda goes as b t to the power 2/3. So lambda dot over lambda is 2/3 b t to the power minus 1/3 divided by lambda is h. So h inverse lambda inverse goes as 3/2 b inverse t to the 1/3. Right? So it again grows. Okay. So the net upshot is that during inflation, this H inverse lambda inverse is decreasing, whereas during radiation and matter domination, it's increasing as a function of T. Want this to be as large as possible.
Because H inverse lambda inverse determine the scale to which fluctuations can, I mean, the largest correlation means.
Exactly. H inverse lambda inverse determines the largest scale over which you can have correlation.
And you want this to be as large as possible, right? Because you said there's some scale invariant.
Okay, we'll see what you want, right, in a minute, right? But first, let's just plot this. So we plot H inverse lambda inverse against T. So this is a co-moving distance, right? This is all measured in the co-moving distance. H inverse lambda inverse is a co-moving distance that light travels. So what we see here is that it goes like this. This is our TF. Then, okay, let's ignore this reheating part, right? Assume that it's radiation, then it starts increasing as radiation, and eventually it becomes matter. Slope changes a little. Well, I'll actually draw it like this. So this is the equality of radiation and matter. This is the end of inflation, right? Then it started growing as radiation dominated, and this is the equality between radiation and matter. And this is the last scattering.
So what happens to the curve at last scattering?
Nothing. Not just grows, because you have that it's matter, it has entered matter domination, right? So this H inverse lambda inverse grows as matter domination. Let's call this R naught, okay, the value of H inverse lambda inverse at the time of last scattering. Okay. So this R naught is something you have encountered before, right? I mean, what is the significance of R naught? Yeah, so this R naught is what corresponds to 2 degree in the microwave sky, right? Because the fluctuations at that scale, okay, the H inverse and lambda inverse is the fluctuation at that scale, right? So we see that those fluctuations can affect distances up to R naught, right? This is telling us how to what distance you can affect, right? And we had already argued earlier that the fluctuations in the microwave sky, fluctuations after inflation, right, can affect distances up to 2 degrees, right? So this R naught must be that distance.
You wanted some scale invariant fluctuations, right? I thought we made the statement that 2 degrees was not special.
Yeah, we are not, so we want scale invariant fluctuation. We are not trying to say where it comes from, right? We are just trying to see what scale fluctuation can be affected by what physics, right? So scale at R naught, right, can be affected by fluctuations over length scales, right, in this region. See, what is special about this region between this and this, right? That H inverse lambda inverse is below R naught, right? H inverse lambda inverse is below R naught, right? Which means that the fluctuations at a given point affect scale up to H inverse lambda inverse. Okay. So what this is saying is that I think something is wrong here. So the idea is that this, okay, let's look at the various other values. It's R1 and the R2.
R2 is the
Some value. R2 is larger than R0, this is less than R0.
less than T, the T equilibrium, T equality car also.
Exactly. Okay. So what it is saying is, suppose we look at fluctuations at scale R2. Yeah, fluctuations at scale R2, right? Okay. Those can only be affected by, you have to have produce fluctuations at that scale, right? That length scale. Okay. You see that all the way from here to here, right? The fluctuation, this is the fluctuation scale, right? This is below that curve. See, this curve at the time of last scattering remains below R2. Is that clear? Look at the H inverse lambda inverse, right? It's below R2. In this, from here to here, right? The maximum length scale that the microscopic physics can affect remains below R2, right? So fluctuations at length scale R2 cannot get any contribution between here onwards. Is this clear? It's too big, right? If the scale is too big, right, H inverse lambda inverse doesn't exceed that scale. Where H inverse lambda inverse was falling earlier, right, and now it's growing, right? At the time of last scattering, that's what we are seeing the sky, right? H inverse lambda inverse from inflation to here is always remains below R naught, right? So it cannot affect fluctuations at scale R2.
Drawing the curve from very top.
Because it falls during inflation, right?
It falls, but we don't know from what value.
Yeah, we don't know for what value it falls, but it falls from some value, right? So as long as the number of e-folding is larger than 10 to the 50, right, this goes above. Right, so that's what determines that this at least has to go above or not.
The statement you're making here is that this fluctuations at R2 scale cannot be produced by anything in between those two times.
Yes.
Anything?
After inflation. Because you stop here, right? After that, what happens, it doesn't matter because you are seeing the last scattering surface. Fluctuation that you are observing is the last scattering surface, right? So what happens after that doesn't matter, right? Up to the time of last scattering, right? Anything that happened after inflation is below this R2 scale.
So it cannot be produced between, say R2 was at T2.
R2 was at
R2 intersects the curve.
At T2, yeah. So after T2 it may produce, but that's irrelevant because T2 is larger than last scattering temperature. Oh, here. Oh, yeah, indeed.
So in between T2 and the last scattering,
yes,
you can't produce any fluctuations that are
exactly, right? You cannot produce and you cannot affect fluctuations at that scale, right? So any fluctuation at scale R2 must have been produced before the end of inflation. Is that clear?
So this fluctuation will be produced before this T2 time.
Before T2, exactly, right? So this is what is called the exit, that fluctuations exit the horizon. Okay, so this is what is called exit of the fluctuation.
Always outside the horizon size in this time.
Exactly, that's
So
right.
it cannot be produced.
So it cannot be produced by the microscopic physics, exactly. Right. Now, what is special about R naught? This is what is cutting the last scattering surface, right? If you take any distance below R naught, say R1, right, what you see is that the R1 in this region, so the fluctuations in this region will not affect R1 scale fluctuation, but between here and here, right? Let's call this some other number, T3. Between T3 and TLS, right? H1, H inverse lambda inverse, right, is above R1, right? So fluctuations at scale R1 could be affected by physics, the microscopic physics, before the time of last scattering. Right? R naught is a boundary, right? R naught is a boundary that so that a fluctuations above R naught cannot be affected by microscopic physics after inflation. Fluctuations below R naught, right, can be affected by the microscopic physics after inflation.
So that's because of the speciality of the time of last scattering.
Yes, exactly. That's because of the speciality of the time of last scattering, right? And that's this 2 degree, right? We said that from earlier analysis we had concluded that the 2 degree is the limit, right? That fluctuations below 2 degree could be affected by fluctuations above after inflation, but fluctuations outside 2 degree range cannot be affected by fluctuations after inflation. Right? So that's the reason why R naught spans 2 degree in the sky, right? Fluctuations at a scale that is below this 2 degree scale, right, are affected by microscopic physics. After inflation, fluctuations at scale above the 2 degree scale are not affected by microscopic physics after inflation.
When we calculate correlation between the region inside 2 degree.
Yeah, indeed we do, right? So if you might have seen the CMB spectrum. So the CMB spectrum is not plotted in the position space, but in the Fourier transform, right? The angular momentum space, right? Instead of the angle space. So there, if you plot the CMB fluctuation, right? This is the delta T over T, and this is L, right? L is the angular momentum. Angular momentum, right? So this is the conjugate to the angle, right? So large L corresponds to small angle, and small L corresponds to large theta, right? So what one finds is that the spectrum looks like this. So this part is above 2 degree, greater than 2 degrees scale. Okay. So this is a direct prediction of inflation, right? You don't need to know anything else other than inflation and classical physics. So predict this part. Okay. This part is above 2 degrees. This is smaller than 2 degrees. Right? So L is larger. Okay. And we see that there is a difference, right? All these peaks are produced because of the microscopic physics that happens here. Right? But you can predict, you know, of course, the microscopic physics, right? You can predict what the shape of this will be, right? And this is what you compare with what you see in experiment.
The finer than 10 to the minus 5.
This is
Everything past that dotted line, that dashed line.
is less than 2 degrees.
Which is finer than 10 to the minus 1 to 10 to the minus.
Well, not finer, it's finer than 2 degrees, right? The correlations are different. Okay, 1 in 10 to the 5, right? That of course is the overall measure, right? I mean, this gives the detail of the spectrum, right? And the angular and the Fourier transform space. Okay. So finer doesn't mean that it's very much larger or very much smaller. L is the angular momentum.
What angle are you talking about? It's the conjugate of what angle?
The theta angle between the 2 points on the sky. Right? So what we calculate is this, right? Delta t over t at theta, delta t over t at theta prime, and we calculate the expectation value over the sky, right?
So this is for some azimuth,
For some?
for some phi, for some azimuth.
No, everywhere in the sky. So theta phi, okay, if you were put theta phi. So there is an angular, because of the isotropy, there is angular momentum conservation. So there is delta LL prime. This is what we are asking. So the fluctuations obey isotropy, right? The fluctuations do obey isotropy, right? So when you convert it to the Fourier space, there is a angular momentum conservation. L and L prime have to be equal. Right? Delta LL prime, delta MM prime, and this is the coefficient of that delta LL prime term once you do the Fourier transform. Yeah, this is a delta t over t correlated, exactly. This 2-point function converted to the angular momentum space.
This is the position, the delta t.
Yeah, the amplitude. Exactly, this is amplitude, right? And the amplitude, as I said, so this part is what is the scale invariant spectrum. Here you can see that it starts oscillating, right? But all of these can actually be predicted, right? The inflation. So what you will see is that the inflation, right, in this part produces scale invariant spectrum. Right? So it produces scale invariant spectrum, then they keep exiting the horizon, right? As it produces at various scales, right? Once they exit the horizon, right, they just get frozen. They just evolve classically because no microscopic physics can affect that scale, right? This is what is called a re-entry, right? This is called re-entry, right? Because if you fix a scale R1, right, after this time, okay, microscopic physics starts affecting the perturbations. But it affects in a controlled way, right? And that's what produces these oscillations.
R1 is some arbitrary point that you have chosen.
I have chosen, yes, right? Just to distinguish between what happens for R larger than R naught and less than R naught, right? R naught is special because that's the last scattering surface.
Re-entry happens at T3 until some TLS. That's
Yes, after TLS you don't care because the perturbations have gotten frozen in the microwave sky, right?
That is also less than R0.
Which is less than R0?
After that re-entry.
Yeah, this is R1 is fixed, right? We're just trying to see, and the co-moving distance R1, what kind of fluctuations are produced, right? What kind of fluctuations can affect the fluctuations at scale R1, right? And the point is that in this region, of course, it can affect, and in this region, the microscopic physics can affect it, right? So the physics is that the fluctuations are produced here, right? And then they get modified once they enter the horizon, right? And that modification is what is producing these oscillations. Only of the? No, inflation produces fluctuations everywhere, at all scales.
Yeah, but now that, like after the re-entry,
Yes.
fluctuation.
Yeah, so re-entry happens only for less than 2 degree ones, indeed, right? That's why these oscillations start after certain value of L, right? In this part, it's just purely inflationary physics that we are seeing, right, which is coming here. So that's this part. So explaining this part is easier, right? Explaining this part requires taking into account what happens after re-entry.
Fluctuations are there outside to the
Fluctuations are there outside 2 degree. Inflation produces a fluctuation, right? Inflation has no problem producing fluctuations outside 2 degree. Because even here, R2, which is larger than 2 degree, right? Early enough, right? The H inverse, lambda inverse was bigger than R2, right? So at that, in that period, the fluctuations could produce.
But the fluctuations greater than 2 degrees, they are not correlated.
They are not.
There is
They are correlated because inflation correlates them. Whatever physics produce them during inflation, right, correlated these fluctuations over large distances, right? It's only after they exit the horizon, right, that they get frozen, that no further microscopic physics can correlate them.
okay, so microscopic physics can't explain the fluctuations that are there outside 2 degrees.
Microscopic physics in this part cannot explain the fluctuations that are outside 2 degree, right? But the microscopic physics during inflation explains everything, right? Because the number of e-foldings is chosen in such a way that inflation smoothens out over that scale, and that also means that inflation also produces fluctuations over that scale, right? Whichever scale the inflation smoothens out, right, is also the scale over which the inflation produces fluctuations.
This part of the graph, whatever fluctuation we see, that is then it's basically scaled out to all scales because it doesn't show. It's frozen.
Because of this part.
That this is
Yeah, so this is a part that has gotten frozen after it exited the horizon during inflation, right? After that, it has never entered the horizon, so it remains unaffected.
then when it comes less than 2 degrees, then it re-enters the horizon size and then
Exactly, right?
microscopic physics can modify it.
Exactly, right? And this is the modification due to the microscopic physics. Yeah, so that requires some effort to show, right? But once you take into account microscopic physics, one can show that there will be oscillatory peaks like this.
When now let's say before exiting the inflationary phase, there also we should see some oscillation.
No, there is scale invariant spectrum. Inflation produces scale invariant spectrum, right? Yeah, you don't see any oscillations. Inflation produces only this part of the spectrum, right? The oscillations come because of the microscopic physics after inflation, right? After the entry.
Interpreting this graph in theta and phi, you are saying as you go finer, smaller and smaller theta and phi separations, there are scales at which the correlation functions achieve maximum.
Exactly. Right? This is what is called the baryon acoustic peak, that the microscopic physics is just and roughly the idea is that once these things come inside the horizon, right, it produces something like a sound wave in the medium, right, because there is a plasma, right, of the that is sitting there. Right? So the sound wave, so basically in that medium it produces a sound wave, these fluctuations, right, and that sound wave is responsible for these peaks, all the peaks.
Why is it a sound wave?
Because it's a disturbance, right? The disturbance was not interfering with the microscopic physics before it re-entered, right? But once it re-enters, right, it's as if it's producing a disturbance in the medium. And that spreads out. And that spreading out effect is this producing these oscillations. So I'm not sure that in this course we will study this part, but we will certainly study this part of the graph, right? What inflation produced in the early universe. Right? But as I said, this part is also well understood. Right? It basically requires analyzing standard classical physics, right? Taking into account the fact that the H inverse lambda inverse has become larger than the scale at which you are working.
Less than 2 degree part will go large L. Large L is
Large L, yes. That means smaller and smaller angles.
This spectrum remains, keeps oscillating at larger and larger.
Yeah.
Doesn't relate.
When your amplitudes go down, right? So in a sense, asymptotically, it just becomes a single one. It's like different harmonics are being excited, right? That's the cause of this.
So, I mean, is the envelope going down or is the?
It's going down, yes, indeed.
What is the reason for having this resonance in that particular angular momentum mode?
Well, that depends on the, I mean, you can work this out, right, from the equation of state. Because you just disturb a plasma, it has some natural frequency in which it spreads out, right? So it's basically determined from there.
Just regarding this X inverse lambda inverse curve, it is time. In all these values, we know the overall behavior of the curve, but we don't know from where it starts. So by using this curve, can we constrain some of the starting points of at what point the inflation should start, such that we should have.
Well, the only thing that we don't know from microscopic physics is the overall amplitude. This part of the curve we know, right, except for the overall shift, right, the amplitude of the, I mean, 1 in 10 to the 5 we don't know, right, that depends on the parameters of inflation, right. So that helps you fix the parameters of inflation, right, this is 1 in 10 to the 5.
Parameters of inflation as is the cosmological constant is that.
Cosmological constant at that time in particular, right, and the scalar field self-coupling, for example, right, all those parameters affect this.
Other than that, this A, B, C parameter, for example.
Yes.
The inflation, the C inverse, that C inverse will determine from what that R2 is.
Yeah, so the C is not very important, right, because the C actually you can absorb inside T, right, you can, by shift of T you can kill the C, right, so C is not really very important, right, H is important, and then the scalar field couplings are important because it's a fluctuation of the scalar field which produces this. Okay, so we'll continue next time.